All right, so good morning, grade 12s. Guys, I'm so excited. I actually took a long time to put these notes together for you. This is a really, really great lesson on something called thin film interference. Now, I want to tell you before we start that, we've been talking in this entire unit how light behaves like a wave and how Huygens was right 300 years ago. And the key point for when we knew Huygens had to be right is when we discovered interference of light. Well, thin film interference, okay, as we'll see later today, I can tell you right now that they would have seen thin film interference 300 years ago when Huygens and Newton were alive, but they didn't know it was interference. Okay, so there were thin films back then. Like if you can make soap and have soap bubbles, you see thin film interference in soap bubbles all the time. That's just property of soap bubbles because the soap makes a thin film. Anyway, I'm going to show you some familiar examples here of this that we see all the time. You see all around you every day. Okay, if you went outside today, you could probably see some examples of this. Yeah, if you clean the dishes, you'll see some examples of it. So anyway, lots of examples. Looking at birds. Birds have thin film interference too. Some insects have thin film interference. So we'll talk about all of those things. Okay, so first, before we can talk about thin film interference, we have to first talk about something called boundary behavior. So what happens when a wave hits a boundary? Well, here we have a wave hitting a wall. Okay, and as you can see when you look at this wave, what happens to it after it hits the wall? Well, it reflects. But something changes when it reflects. It changes phase. Okay, so the crest becomes a trough. Now, if I'd started with a trough, it would become a crest. So, in other words, here we call this is a hard boundary or a fixed end. Okay, like it's fixed to the wall, the end of the string, and we get something called a phase inversion on reflection. Okay, so in other words, a crest, for example, becomes a trough. And that is hard boundary or fixed end reflection. Now, what happens if you don't have a hard boundary, but you have a soft boundary? So this is a soft boundary, and here you can see with the wave, its end is free to move, like it's not fixed to the wall, so it's sort of like attached to a pole or something, and it's free to move up and down. So we call that a soft boundary, or a free end, okay? And what you can see in the soft boundary here is that we have no phase inversion. I'm going to underline the word no. There's no phase inversion this time. The wave stays the same, so a crest, for example, stays a crest. All right, so that's called boundary behavior for waves. What happens when they reach a boundary, okay? And we can see that the reflected waves do one of two things. They either get inverted or they don't, depending on if the boundary is hard or if it's soft. All right, so now, that's pretty straightforward, by the way, okay? So now let's talk about refraction. Refraction, this is a little review of refraction. We've talked about this before, but just to review the concept one time here, because we're going to need this, all these things for thin film interference. Here is the wavelength in the incident medium, and here the the wave enters the water and slows down. So this is a light wave entering the water, let's say. And when it slows down, the wavelength gets reduced. Okay, now there was a formula that for light when we talked about refraction where, I should tell you this is the faster medium, right? This is the slower medium down here. And that's why the waves refract towards the normal, because they're slowing down. Now for light, the index of refraction for the medium, this is we did before, okay, is equal to the speed of light in a vacuum divided by the speed of light in the medium, okay, where c equals 3.0 times 10 to the 8 meters per second divided by whatever the speed in, oh sorry, what am I saying divided by? That's the speed of light in a vacuum. All right, so next, I'm going to change this. I'm going to use the formula V equals F lambda, okay? The frequency does not change when you enter a new medium. So I'm going to write frequency times the wavelength V, okay, where the wavelength V is the wavelength in a vacuum, okay, and divided by F times the wavelength in the medium. Now those frequencies are going to cancel out because frequencies don't change. So that is a new formula for the index of refraction, that Nm is equal to the wavelength in a vacuum divided by the wavelength in the medium. All right, I'm going to put a little box around that. We're going to need that later, okay? So that's the definition of the index of refraction. It's the ratio of these two wavelengths, okay? The longer wavelength, let's say this is air, it's more or less like a vacuum, okay? Where the index of refraction would be 1.0, okay? And here the index of refraction for water is 1.33. So in other words, the waves go like they're 1.33 times, like the speed of light in a vacuum is 1.33 times faster, okay, than the speed of light in the water, okay? So that's what the index of refraction means. But here's a way of calculating it, okay? And we're going to need that later. All right, now let's go to color theory. Now we didn't really talk about color theory before. You should have done it in grade 10. So I'm going to talk to you about it right now. You're gonna feel a little. Anyone who's taken art will disagree with me and everything, but I'm telling you the truth, okay? So look, if you have light sources, we call this additive color theory. So this, additive color mixing. I'm gonna underline the important words. Light sources. In other words, this is a green light. I use black. This is a green light. This is a blue light, and this is a red light. And we shine these three lights so that they're overlapping the way you see here, okay? What you'll find is that red and green make yellow, and I'm not talking about paint. I'm talking about red light shining on a white wall, okay, mixed with green light. So if I have a red flashlight and a green flashlight, and those two lights overlap, okay, where they overlap, you get yellow light. Okay, where green and blue overlap, you get cyan. Okay, where red and blue overlap, you get magenta. Okay, and then finally red and green make yellow, and all three, red, green, and blue, together make white. Okay, now these are for light sources. Now, what about paints or pigmentation? Okay, so here's the deal. We call this subtractive colors. See, pigments aren't light sources. They're not luminous, you see. Like, they don't emit light. Like, so say, for example, you had a can of paint. Let's say, for example, we take a can of paint. Okay, we're in a classroom, and we throw the paint on the wall. Okay, whatever. Little vandalism for you. But then we turn out all the lights. Will you be able to see the paint that you threw on the wall? Well, of course not. Okay? You won't be able to see it because paint is not luminous. It's non-luminous. It doesn't emit its own light. It only reflects light, okay? Now, red paint looks red for this reason. It looks red because it absorbs green and blue light, okay? So if you look at additive color theory, red plus green plus blue make white. So if you have white light, which is normally the light that we have in the room, right? When we turn on the lights, that's white light. When white light hits red pigment, okay, like if I'm wearing a red shirt, if it hits my shirt, then what happens is the green and blue light gets subtracted by my shirt. So my red shirt actually absorbs green and blue from the white, and the one color that's left is red, okay? Now, a blue shirt would absorb red and green. A green shirt would absorb red and blue, okay? And that's why it looks green. But a yellow shirt, okay, only absorbs blue, and it reflects red and green, and so the shirt looks yellow, okay? based on what it reflects. Okay, so what it's doing is subtracting a color from the white light, okay, then that's why we call it subtractive color mixing, okay. So here's the deal. These are pigments, okay, not light sources, but pigments, or paint, if you like, okay. Now, I don't know how it works in art class. I always forget. They'll say red and blue make, whatever. I don't know. Red is one of the primary colors. That's actually not true. Okay, the primary pigment colors are yellow, cyan, and magenta. Okay, and if you were to mix yellow and cyan paint, you would get green. Okay, why is that? It's because this one, okay, let me explain. This one absorbs blue. Gosh, I had to think about that for a second. That one absorbs blue. This one absorbs red. Okay. And that one absorbs green. It subtracts, okay, those colors. Now here's the thing. White light, okay, so I'm just going to I want you to remember this. White light is red plus green plus blue, okay? Now why is white so important? It's because the sun basically produces white light, okay? The light bulbs in your house produce white light. Basically we're used to seeing the world illuminated by white light, okay? And so white light is red plus green plus blue, okay? And then what happens is, if yellow absorbs blue and cyan absorbs red, when you mix them together, you're subtracting like here, if you have red, green, and blue, but the yellow absorbs the blue, so we'll cancel that one out, okay? The cyan absorbs the red, so we'll cancel this one out, right? And together, cyan and yellow make green, okay? That's the only one that's left. So that's how subtractive color theory works, okay? One more thing about this, I'm just going to say note on the spectrum, on the visible spectrum. Okay, so on the visible spectrum, red, so we have red, I gave this to you before. Okay, so here's your colors on the visible spectrum. This is around 700 nanometers. Let's round it to 800 nanometers here. Here in the middle is around 500 nanometers here. Okay, and then down here we're down around 300 nanometers on the violet side. Okay, so from long to short, that's your range of wavelengths. Okay, and here you can see red, orange, yellow, green, blue, violet. These are the colors of the rainbow. So according to wavelength. So we go from longest at red to shortest at violet. Okay, and that's it. All right, so now that we've seen boundary conditions with reflection of waves, that's pretty easy. We've seen how refraction works and this formula for refraction where you change speeds in the new medium here. And we've seen how color theory works. So now that you've seen these three things, now we're ready to look finally at thin film interference. So armed with this knowledge, okay, let's now look at thin film interference. Now, I actually took this picture myself, I think in the school parking lot actually, some time ago, like a few years ago. And today the roads are, well, they're drying out now, but they were wet this morning because we had some rain last night. So, and if you go out in a parking lot, and it's especially in a parking lot, okay, when the roads are wet, you'll often see something like this. Now, I know you've seen it because we've all seen it, okay? Anyone who's been in a parking lot on a rainy day or after a rainfall has seen this before. So what are we looking at here? Well, it's actually a drop of, like, you've got someone who's got some dripping of oil or gasoline from their gas tank, Okay, so you won't find this under my Tesla, of course, but you'll find it underneath gas-powered cars, right? So what happens is you have gas in the tank, and older cars will sometimes drip oil or gas onto the asphalt. Now what you're seeing here is a mass of gasoline sitting on top of the asphalt. Now it's important that the asphalt is wet, okay? Like this is wet asphalt. You won't see it if it's dry, okay? And there's a reason for that. Now I've got another couple of pictures here to show you. Oh, actually that's a video, and we'll talk about that in a second. So here's the thing about this. Newton and Huygens would have seen this during Newton's time, but you know, they didn't know this was an example of interference of waves. So here you can clearly see bands of color. Now, the reason why I had to teach you about color theory is you really see the secondary light colors dominate. So in other words, you see cyan, magenta, and yellow, okay? Like here is a very clear example. If I zoom in a little more, that's cyan. Here we can see magenta. So this is magenta, that's cyan, and then we see yellow, okay? Now, in fact, the first band that we see out here is on the yellow side, okay? So here we see something that looks yellowish, okay? And then that transitions into what appears to me to be magenta, okay? And then here we see cyan. And then it repeats, yellow, magenta, and then cyan, okay? And we see yellow, magenta, cyan, these bands, these repeating bands of color. So why? What's going on here? How is this explained by, I'm going to come back to this picture shortly. And by the way, on the outside, we see white. Okay, now the clouds in the sky are typically white, okay, or at least a white light coming from the sky. So that is a reflection of the sky, basically. Okay, the overcast sky is usually after a rainfall. All right, so there you go. That is an example of thin film interference. Now there are other examples, okay, that I'd like to show you. But before we do that, I wanted to show something here. I don't want to show you this whole video, but I want to explain using this video how thin film interference happens, okay? So let me see if I can do that. And I don't want any audio from this guy. Okay, so I'm just going to let it, see if it'll let me do this. All right, right about here. Okay, so here's the deal. I'm going to let it play in a moment. You're going to see some waves that are going to, here, I'll narrate it as the guy shows it, watch. So here's a wave, it bounces off the top, okay, of the film, then it goes through and part of the wave bounces off the bottom layer, okay, and then there's some light that makes it through. So imagine this is a film of gasoline, okay, and there's water underneath it. So what's happening is you're getting two reflections, one off the top and one off the bottom. Now those two reflections, okay, have a path difference. So here we can see the wave action that's happening. Now those two reflections can produce interference. See that constructive or destructive interference depending on the wavelength of the waves and the thickness of the film. Okay, so it takes two waves to interfere. So here we see that these two reflections can produce interference. Now he's going to show you some examples of glass that's treated with an anti-reflective coating. We'll talk more about that later. Anti-reflective coatings are an application of this. But let's just pause it here for now. Okay, and let me get back to our soap film. Okay, so here's the deal. How can we get our heads around this? And in fact, this is the really cool part now. We're going to figure out exactly how thick the film is at the first yellow band. So here we see our first yellow band. If I ask you this question, all right, how thick is that film right there, guys? Like, exactly how thick is it? In nanometers, okay? Or like, we know it's incredibly thin, right? Like very, very thin film, but just how thick is it, okay? Well, here's the deal, you can figure it out. In fact, we can figure out the thicknesses at each of these bands. So here we have another yellow band right there. How thick is it there? We're going to answer that question too. Okay, so And by the way, what you don't see, there's something that you're not seeing on the very edge outside of this white area. The film is there too, but it's invisible. Okay, and I will explain that in a moment. All right, so let's look at our method. Now, in order to understand this method, I'm going to lay it out in steps for you. Okay, so our question, I should write the question, just so we don't lose sight. How thick is the film? At the first and second yellow bands. Okay, so that's our question. Okay, let's see if we can do it. Now here's our method. Number one, okay, we're going to examine the phase of the reflected waves. Okay, now you're not going to like how we do these problems because it's not just an equation that you use. It doesn't really work that way. So it works, you have to do this method. Now I'm going to draw a diagram. You don't have to draw the diagram to get this. The diagram is going to look like what I showed you in the video. Okay, so here's the deal. We have air on top where the index of refraction is 1.0. Here we have gasoline where the index of refraction is 1.42. Now I've looked these numbers up. These numbers would be given in the question. And underneath is water, where the index of refraction is 1.33. Okay? So here's the deal. When light comes down from the sky and strikes the film like that, okay, when it reflects, it's going to reflect off the top. So I'm going to put a black wave here. That's just a plain reflection. But here's the deal. Because this index of refraction, we'll call this N1, N2, and N3. So because N2 is greater than N1, the first boundary is a hard boundary. In other words, like gas is more dense than air. Okay, and so what happens is it's like hitting a wall when that wave enters the gasoline, okay, and some of it reflects. So therefore, like the ray number one is inverted. Now, why? How do we know this? It's because it's a hard boundary. And the first thing I told you today is what happens to a wave when it hits a hard boundary. So I'm just going to write down up here that this wave is inverted. Okay, so we're still on we're doing step one. This is really easy step. Now I'm going to use a different color. This wave is going to refract also through the medium, and then it's going to bounce again off the bottom layer. Okay, and then it's going to sort of come out and exit like this. And it's those two waves that interfere with each other, you see. Okay, like that's the thing. Now this blue ray that I've drawn, does it get inverted? Well, let's take a look. So here, the gasoline, N3 is less than N2. So in other words, the water is less optically dense than the gas. Okay? So remember, we have air on top, gas, and then we have, you can color it blue down here, is water underneath it, okay, on the wet pavement. The water is less optically dense, so it's got a lower index of refraction. So this is therefore a soft boundary because it's hitting something, it's in the gas, which is more dense, and it's bouncing off something less dense. Okay, so it's important that you understand how I'm making this decision. This is a soft boundary. So you just look at these numbers to decide. Okay, if N3 is less than N2, in other words, if it starts in a medium that's more dense, bounces off a less dense medium, okay, if you want, here, This is fast. This is slower here, and this is faster here. So if you're bouncing off a slower medium, you're going to invert. Okay, that's like hitting a wall. But if you're bouncing off a faster one, that's a soft boundary, and you get no inversion. So ray number 2 is not inverted. Okay? So this one here, I'm going to use blue color, is not inverted. Okay? So here's the deal. I'm going to draw a conclusion now. I'll put in my rainbow color. Therefore, ray 1 and 2 are out of phase. Okay? So one is a crest and the other one's a trough. Okay, so that's step 1. You have to make that decision. It's actually a really easy step to do on all of these problems, and we'll do some more examples. This video is going to be a little longer than normal today because thin film interference is a big topic. Okay. All right, so that's step 1. We see that the first wave is inverted, and then it splits off into 2. The wave that goes down to the bottom here is not inverted when it bounces off the water. Okay, now you're the observer, you're seeing these 2 reflections, but they interfere, okay, and produce interference. So now, step 2, and there's only 2 steps. Okay, once you made that first decision, step 2. By the way, I'm going to assign a variable here. I'm going to say that this T, where T equals the thickness of the film. Remember, our goal is to determine the thickness. Okay? So now, what we're going to do in step 2 is we're going to, okay, actually I'm going to change my mind. I'm going to make 3 steps. I'm going to break it down just slightly more to make it easier for you. We're going to determine the wavelength in the medium. Okay, now this was what I showed you earlier with refraction. The wavelength in the medium, and the medium here is the gas. Okay, gasoline. So the wavelength in the medium, we already know, okay, is going to equal the wavelength in the vacuum, okay, divided by the index of refraction in the medium. So that's going to be 1.42. Okay, now we're just going to leave that alone because we're not going to solve yet for the wavelength, okay, or anything. We're not going to use a wavelength just yet. Okay, and I'm just going to say note. Because it's a yellow band, yellow is red and green light. So yellow, okay, we already know that yellow is equal to white minus blue. And so for blue, we're going to use 300 nanometers. That's violet, but we're going to say it's blue and violet very close to the same wavelength. Okay? So what we're doing when we see a yellow band, okay, I'm going to say a yellow band equals destructive interference. We're subtracting it, so it's destructive interference for blue. So what we're seeing at the yellow band is one color is being subtracted. Well, if blue is being destructively interfered with and the other colors aren't, you're going to see a yellow band there. Okay? So step 2, we're just going to think about that for a second. Why do we see a yellow band? Well, that's why. Okay? Now, step 3, I didn't leave myself enough room. I got the soap bubble example coming up in a moment. I just need to make a little more room for myself. Here, just bear me for a second while I move this. Okay. So let me move my soap bubble example down a little. Where's that? Okay. I'll fix that later. All right, let's come back here. All right, finally, our last step, step 3. Step 3 is to finally to answer the question, okay? But we're going to examine cases for constructive, destructive interference, okay? So here's the deal. We know here, case 1, we're looking for cases of destructive interference. So let's do that first. We're trying to find a destructive interference thickness for blue, right? So let's do destructive interference. And we'll do constructive interference also. Like sometimes you'll see a bright green. Why are you getting that? Well, sometimes you get constructive interference. It depends on how thick the film is. Okay? So let's do destructive. Now, we know that for waves, because these waves are out of phase, so because of step 1, because the waves are out of phase in step 1, okay, that means if the path difference equals approximately 0, we're going to get destructive interference. I'll talk about what the path difference is in a second. And that's because of step 1. They're out of phase. And that means you have a crest and a trough, right? So you have crest. So ray 1 is a crest. Ray 2, not ray squared, ray 2 is a trough. That means they're out of step already. So if they're right on top of each other and the path difference is approximately 0, we're going to get destructive interference. Now, where is the path difference approximately 0? Now that's going to be true, by the way, destructive interference for all wavelengths, for all colors. All right, all wavelengths for you physicists out there, okay? Wavelengths equals color. Okay, so here's the deal. Where do you get a path difference of 0 on this film of gasoline? Well, you're going to get that on the outer rim. So like you see this white band here, okay? So the white is a reflection of the sky. That's not what we're talking about. What we're talking about is an invisible film. Like, so right here, this is where the film is incredibly thin. And here, your path difference, right there, okay, right at the edges here where you don't see anything, is approximately 0. Now there is film there, but it's just super thin, okay? And it's totally invisible. You don't see any reflection from it whatsoever. Now, it's so thin, okay? And what we mean by that, okay, with your path difference being approximately 0, we mean that the thickness doesn't have a thickness of 0. We mean that the thickness is way less, okay, than the wavelengths for visible light. So let's say it was 3 nanometers thick. Well, that's way less than 300. And that's basically the waves are on top of each other, okay? All right, so for visible light, like that. Now, here's the deal. What do we mean by path difference in the first place? Well, let's look at our little film here. This guy, this blue wave, has to go down through the film like this and then back up like that. And we're going to pretend that the light is pretty much coming straight down. I know I've drawn it on an angle so you can see it. But the path difference here in this diagram for the blue wave compared to the black one equals 2t. It's twice the thickness, right? Because that blue wave has to go down through the film and come back up. Now we're going to assume it doesn't move much laterally. I know you don't like that. Remember, this film is incredibly thin, right? And so really, how much sideways will it move, okay, at an angle of incidence that is pretty close to 90 degrees? And the answer is it basically won't move laterally at all, and these waves will still be right on top of each other. So I know that's an approximation, but trust me, that's how we do it. Okay, so now we found a case where for all colors, Okay, and this will give us edge, the outer edge where the film is thinnest, the outer edge, okay, of the oil film is just completely transparent with no reflection at all. Okay, so that is what we see, okay, all around the edge. You're not going to believe me that it's even there because you see this white edge and that's the first thing you see, but trust me, there's film that extends beyond that you just can't see at all. That is what we are seeing there. All right, now next, another case for destructive interference, because these waves are out of step, if the path difference is a wavelength, then they'll stay at a step. So if I take one wave and shift it over a full wavelength, well, they were out of step to start with when the path difference was 0. So at a wavelength, they'll still be out of step, okay? And that'll give you destructive interference for a certain wavelength, okay? Now, here's an interesting case. So if the path difference is equal to a wavelength, we'll get destructive interference. They're still at a step, okay? Now, what we're going to do is we're going to solve this case. Okay, 2t equals the wavelength. So how thick is the film? Well, it would equal the wavelength divided by 2. Okay, now here's the thing. We need to use the wavelength in the medium. Okay, so this is while it's in the medium, and that factors in the differences in speed. So we did step 2. Okay, so here in step 2, from step 2, not strep, what are we doing? From step 2, we have the wavelength in the medium equals the wavelength in the vacuum divided by 1.42. Well, we're looking at blue, so that's 300 nanometers divided by 1.42. Now, by the way, we always quote wavelengths in a vacuum. So when I say blue is 300 nanometers, that means that's what it is in a vacuum. In the oil, it will be a different number. Okay, so I'm going to take this number 300, and I'm going to divide it by, I'm going to leave it in nanometers, by the way. Don't bother, don't put times 10 to the negative 7, you don't need to. So I'm going to go 300 divided by 1.42. So my answer will be in nanometers. That's 211.27 nanometers. I won't round it too much. And now we get to this point here where we can say this. So that's equal to 211.27 divided by 2. So I'm now divide my answer by 2, and I get 105.6. 105.6 nanometers. So get this. Here, blue will be subtracted at 105.6 nanometers of film thickness. So what we just did is we figured out, and that is our first yellow band. So we just figured out, when you're looking at this oil film, where this first yellow band is that I've marked here with a yellow, right here, I'll do it here with my rainbow, right there. You can see it all around here, this yellow band. That first yellow band, okay, we see a little bit of white. Now, by the way, the white occurs because like the film just isn't the right thickness for any destructive or constructive interference in between 0 and when we get our first yellow band. And so all the colors kind of get reflected the same amount, and therefore we see some white, the reflection of the sky. But then when we see the first yellow band, that yellow band is 105. Okay, let me use a different color because this is not working. I'll use black. So this yellow band is 105.6 nanometers thick. Now, use a little common sense. The oil drop will be thickest at the middle, and then it's going to get thinner as the oil spreads out. So that should be logical to you. Okay, so what we're seeing here is, here the film is thinnest here, and it's getting thicker as you go inwards. That's why we see these bands, right? So our first yellow band, that's 105.6 nanometers of thickness. That's how thick that film is right there. So cool. We figured it out right there just based on the colors that you see. And we need a little knowledge of index of refraction and wavelength. Okay. Now what I'm going to do is I'm going to go next to this. Okay, because I don't want to scroll away anymore. And I'm going to talk about the second yellow band. Okay, so this was the first case of destructive interference if the path difference is a wavelength. So here, case 3, what if the path difference was 2 wavelengths? Okay, well, you're going to get destructive interference again because the waves are out of step. Okay, so what you're going to do is you're going to write, okay, so 2t will equal 2 wavelengths in the medium like this. The path difference is always twice the thickness. You cancel out the 2 this time and you end up with t equals just the wavelength in the medium. Well, the wavelength in the medium is 211.27 nanometers. That's for blue light. So blue light will be subtracted again when the film gets to 211 nanometers. So here, this second yellow band, is 211.7 nanometers of thickness. Did I say 0.7? I don't remember what I said now. 0.27, pardon me. So 211.27 nanometers of thickness. 0.27. And that is the second yellow band. Now, we could keep going. There should be a third yellow band, and you can kind of see it right in here. So there's our third yellow band. And, we just could keep going. Okay, we can just keep doing new path differences. So if I do another path difference, step 4, what if the path difference was equal to 3 wavelengths? So you get the idea, right? Okay, therefore 2 twice the thickness is equal to 3 wavelengths in the medium. So the thickness would be 3 over 2 times the wavelength in the medium. Well, the wavelength in the medium, is 211.27. So 211.27 times 3 divided by 2 equals 316.9. And so the third yellow band would be at 316.9 nanometers. Now, eventually the film will become too thick for us to see these kind of banding, and that's what's happening in this region here where you just see the asphalt. Okay. What happens is there's too much sideways displacement, and then the waves aren't on top of each other anymore. So here at the third yellow band, that's going to be 316.9. It looks kind of greenish, but anyway, there's a little bit of yellow in there, right? If you look carefully at it, you can see a repeating pattern. Okay, 316.9 nanometers. So there you go. That is the third yellow band. And we can keep going. Okay, so now we're seeing that like the film starts out very thin, 105.6 nanometers, and then it gradually getting thicker and thicker and thicker as you move towards the middle. All right, so that's our first yellow band. Now what about the magenta band that's right next to it? So let's look at the magenta band for a second. Magenta occurs when you subtract green. Okay, so first we subtract blue. Now the film gets a little thicker, it's going to subtract a different wavelength in between these yellow bands. So when will it subtract, if you want, let's do another example, okay? What about our first magenta band? So like I know I'm going way beyond what the question is asking, but if I do that over here, okay, the first magenta band, and I'm just going to say we have to know our color theory. So magenta is equal to white, red, green, and blue. This is white light, right? Minus green. Okay? So green is approximately 500 nanometers of thickness. Okay? So therefore, we do our case 1, destructive interference, where the path difference is equal to 1 wavelength in the medium. So twice the thickness would equal the wavelength in the medium. So T would equal the wavelength in the medium divided by 2. Okay, now here, we don't just go 500 divided by 2. The wavelength in the medium, we have to first convert it. Okay, 500 divided by 1.42. That compensates for the differences in speed, so we have to do that first. So 500 divided by 1.42 is 352.1. So this is 352.1 nanometers. That's the color green in the gas. Then I divide that by 2. So I got 176. So this is 176 nanometers. So now if I go back up to my picture, I see that this green, or sorry, the magenta band here is at 176 nanometers. 176 nanometers. Isn't that cool? So what we've done is we're breaking down the thicknesses of the film based on the color of these bands. Now we could keep going. I'm not going to waste your time, but you see how it works, right? The next one we see here is cyan. So here we see a band of cyan in here. Cyan is that blue sky sort of color here. You can really see it clearly there. What's the thickness there? Well, for cyan, we have to subtract red. So red has a wavelength of, let's say, 700 nanometers. When are you going to subtract 700 nanometers? Well, you know, I'll just say it. I'll just do it like on my thing here. At first, I'm going to go 700 divided by 1.42, and then I'm going to divide that by 2, and I get 246. So here, no, I didn't do that right. Yeah. Okay, I get around 200 nanometers here. I can't use 700 nanometers. Red starts at closer to 600 nanometers, so I switched to 600 nanometers. And you'll see that it starts subtracting out red very close to when we get our second yellow band. So at around 200 nanometers here, for cyan, we'll see a cyan band. And so we get these colors that you know, sort of alternate like that. Now, what if we were looking for constructive interference? Okay, well, to summarize, I could just write constructive interference will occur. I'm just going to say note. I know I'm all over the place in the notes here, but for constructive interference, to occur, they will occur when the path difference is equal to a half of a wavelength, or 3/2 of a wavelength, or 5/2 of a wavelength, okay, and so on, okay? And we could, if we wanted to find constructive interference for certain thicknesses, we could do it, okay? And that's how you would do it. All right, so that, in a nutshell, is how you do thin film interference questions. I know that it seems really long. I took a long time to explain this video. But actually, let's just do another example, okay? And this one is kind of cool. Let's see if I can move this. Okay, let's do the soap bubble. And let's do it quickly, okay? So just to show you how quick this is, take a look at a soap bubble that's on the top of a soap bottle, okay? And here we see something very similar. So here we see our first yellow band, and then we see a magenta band, and then we see a cyan band, and then it repeats. Yellow, magenta, cyan, and then it looks starting to look green, okay? But anyway, it repeats. Yellow, magenta, cyan, so on and so on and so on, subtracting again, okay? And here at the top, this is really cool, where it's really thin. At the top, I'll use that color here. Here at the top, it looks like there's a hole in the film. The hole is where it doesn't reflect anything. That's when the path difference is approximately 0. Okay? And it just looks like there's a hole. It doesn't reflect anything. Actually, there's no hole. If there was a hole, the bubble would pop. So it's not a hole. It's thin film interference. You don't see the film if you get destructive interference for all wavelengths. All right, so for the soap bubble, I'm going to do the math right next to it here. And watch, I'm going to do step 1. Step 1, we've got air, we've got soap, and inside the soap bubble, we have air again. Okay, air is 1.0. Soap is about the same as water. Well, let's say it's about 1.4. Air here on the other side is 1.0 again. Okay, so you got air, soap, and air. Now, what you do is here you are the observer looking at reflected light. So this is your eye up here. I'm sorry, my eye looks terrible, but whatever. Here's your eye looking at it. Here comes the wave. It hits that. Does that one get inverted? So do step 1. Is ray number 1, is it inverted? Well, here N2 is bigger than N1. So this one is inverted. Okay? And then this wave, which goes through and then comes back up here like this, is that wave inverted? Well, N3 is less than N2, so this wave is not inverted. Sometimes I just put a check mark on them, like I'll say, okay, this one's inverted, that one is not. Okay, so that's step 1. Quick, right? Number 2, we've got to ask a question of some kind. So we'll ask the same question. We'll ask the question, actually, I'm going to change this number a little bit. I think soap is around 1.2, so I'll make it 1.2. So I'm going to ask this question, how thick is the film at the first Cyan band? Okay, so okay, how thick is it there? Well, it's going to be, we're looking for destructive interference. So we'll note that destructive interference will occur because one wave is inverted and the other one is not. They're out of phase to start with. So destructive interference will occur when the path difference, which is again equal to 2t, the path difference is equal to 2t, which is equal to 0, 1 wavelength, 2 wavelengths, 3 wavelengths, 4 wavelengths, and so on. Okay, these are all the cases for destructive interference. If you want, equals m lambda, okay, where m equals 0, 1, 2, 3, and so on. Okay. All right, so the wavelength in the medium. Actually, this is, I'm going to do step 2 and 3 together. Okay, so really this is step 2, and this one is step 3. And I sort of did them out of order. Sorry, I'm trying to go quick, so I'm being inconsistent with you, but it's always the same 3 steps. The wavelength in the medium. Okay, so if we're looking for cyan, cyan equals white, which is RGB, okay, since cyan is green and blue, minus red, and red is 600 nanometers. Okay, so we're looking for 600 divided by 1.2, and 600 divided by 1.2 is 500. Okay, so that's, I leave it in nanometers, I don't change it. Okay, and now to do step 3, we'll do our cases. Case 1, 2t equals 1 wavelength. Okay, so t will equal the wavelength divided by 2. So I'm going to take that number. I get, of course, 250 nanometers. Okay, case 2. If I want another band, I would go 2t equals 2 wavelengths. Okay, and then I'll just get t equals 500 nanometers, right? And then case 3. Okay, and we could keep going. I get 2t equals 3 wavelengths, and then that'll be 750, right? Yeah, I think I've got that right. It's going to be 500 times It's 500 times 3 divided by 2, 750, yeah. All right, 750 nanometers like that. All right, so now let's go back to our picture. See, that didn't take me long. I know this video is very long, but this is a big topic, okay? So every time you see a cyan band, and I'll just color them in cyan, there's one there, there's one there, okay? They're right underneath every purple band, but they're getting harder and harder to see down here. The magenta ones are really easy to see them everywhere, okay? So look, that's case 1 at the top, that's case 1, this is case 2, this is case 3, right? That's how thick that film is, and because the soap film is suspended vertically, it'd be thin at the top and getting thicker as you go down, okay? So it'd be thick at the bottom. So there you go, thin film interference. Now, I was going to leave you with another example, but this video is about an hour long already, okay? You know what though, I think it's only fair that we do a textbook example, so let me at least do one of those. I'm sorry that it's so long, but it is what it is, guys. Okay, I get 3 hours of your time every week. I've only taken like maybe a half hour so far, so now I'm halfway through after this video. Alright, so look, anti-reflective coatings. This is an application, okay, this is cool. So if you have a pair of glasses, anti-reflective coatings, here you can see the man's face with an anti-reflective coating glasses. Here's the same pair of glasses, or a different pair, this time without a coating on it. And you can see aesthetically, the top picture is more pleasing. You can see his eyes better, okay? This one I feel like is not a real image, but anyway, it's a real image of a girl, but I feel like this, the coating here, like the lack of a coating there is not well represented. Here, you can see very clearly her eyes, so there's an anti-reflective coating there. We also use them in binoculars and camera lenses and stuff. Here you can see that this one has been coated with a film of uniform thickness. That's why it looks red, okay? But actually it's transparent, but that's an anti-reflective coating you're seeing there. Here, this greenish hue that you're seeing here is anti-reflective coating on there. So that's kind of cool. Animals. Some animals have, like insects and birds and stuff like that, have thin film coatings on their bodies. Okay, so bird feathers can have thin film coating. That's why this one looks purple. Here we see a butterfly that has like this metallic sort of thin film interference. I'm not sure what the green dot is. I found this picture online. But that blue, like that iridescent color, is always unmistakably metallic almost. Thin film interference, okay? Peacock feathers show lots of thin film interference. Here, the cyan that you can see, there's a magenta and stuff, and these are uniform, and yellow, these are uniform thicknesses. So it's kind of cool. It's not pigmentation per se, it's thin film interference, right? Not a pigment, it's constructive and destructive interference. All right, finally, let me leave you with a textbook example, okay? I promise this will be it. So a film of gasoline floats on water. Yellow light of wavelength shines on an angle of whatever, okay? So it says determine the minimum non-zero thickness so that we get constructive interference. All right, so we already did the gas on film. So let's do step 1, where we look at the phase behavior. We already know that ray 1 is inverted because it goes from air and hitting the gas. And we know that ray 2 is not inverted. And like I say, I just used the check mark. This one is, that one's not. Okay, in my little shorthand. I don't write out the words when I'm doing the problem. Okay, and sometimes I draw the diagram. Okay, that's up to you, but I find the diagram helpful, so you might want to draw it too. All right, so that is step 1. Step 2, we're looking for yellow light constructive interference, and they tell us yellow is 580 nanometers. So the wavelength in the medium will be equal to 580 divided by the index of refraction of the medium, which is 1.4. Whoops, gosh, that's terrible. Don't use the water, right? It's always the gas, like the one that's film itself. Okay, so 580 divided by 1.4. 414.3. Okay, so that's easy. Step 3, we're looking for constructive interference. So we're going to get path difference equals 2t. Constructive interference will occur under these circumstances at a half a wavelength, 3/2 of a wavelength, 5/2 of a wavelength, and so on. Okay, so the thinnest one will be the first one, 1/2 of a wavelength. So therefore 2t will equal 1/2 of a wavelength. Wow. 1/2 of a wavelength. So therefore t will equal 1/4 of a wavelength. So that's 1/4 of 414.3. So I take my answer from step 2 and I divide it by 4. And I get 103.6. So the answer is 103.6 nanometers of thickness. Okay, that's question A. So now, if you do question B, it says, what happens now if we spread the gasoline over glass instead of water? Well, that changes everything. So let's do question B together. And I'm actually going to draw the film. So here we have air on top, gas, and glass on the bottom. So air is 1.0, it's N1. Gas is 1.4. Okay. Glass, it tells us, is 1.52. Okay. Now what that means is, and this is the first time we're seeing this, that the first wave definitely gets inverted. Okay. So this is definitely inverted. The second wave though, the one that bounces off here and comes out like that, that wave now, this number, 1.52, is bigger than this number. And so just like the one bouncing off the top, this one is inverted too. Okay, it's hitting another hard barrier. So this one is also inverted. They're both inverted this time. So this time they're in phase, which means our cases for constructive and destructive interference are going to switch. Okay, so now step 1, we did that. Okay, so we found that ray 1 was inverted and ray 2 was inverted, and therefore they're in phase. Okay, these guys are in phase. So now they're not out of phase to start with. So now we're looking for destructive interference. So step 2. Step 2 is the same as before. Okay, so we found the wavelength in the medium. We're not going to redo the math. We're going to get 414.3 nanometers. So we don't have to do that again. Step 3, and I got that from over here, right? Same step. Because it's still in the gas that we're talking about here. That's still where the thin film is, right? Now finally, step 3. Step 3, our path difference in the cases for constructive interference, because they're in phase, they're going to occur, okay, instead of occurring at half wavelength multiples, they're going to occur at whole wavelength multiples. 0 wavelength, 2 wavelengths, 3 wavelengths, and so on. Now the first non-zero one is that one. We're not going to count that one because it says non-zero. Okay, so therefore 2t equals a wavelength, and therefore the thickness equals the wavelength divided by 2. So I'm going to go 414.3 divided by 2, 207 nanometers. All right, so that is how you do textbook questions on thin film interference, guys. Now this is a big lesson. I realize that I know it's an hour. It's twice as long as my normal lesson. But there's a lot to say and a lot to look at. Now, you can always take these videos or leave them. It's up to you. I put the notes in here. It's probably easier to understand the notes by watching the video. You know, if you want to come back and look at the examples, you can always just fast forward these videos. Before I leave you though, I've done you a favor. Okay, I've made a reference, a guide on how to do thin film interference questions from the homework. Okay, so on the next page in OneNote, you will find a little handy guide for you. Okay, so here it says thin film interference. Step 1, decide which waves. I don't know why it's blurry. Anyway, when you look at it, it shouldn't be that there. Okay, that's better. Okay, so step 1, decide which waves are inverted. Okay, so that's step 1. Now I sort of changed step 2 here. I integrated step 2 and step 3. So here you can see that was step 2 normally. You can see it there also. So I've broken it down into tables, into sort of columns for you. If A and B are not the same phase, so if one inverted and the other one isn't, then these are your cases for constructive and destructive interference. Now, if they are the same phase, then the cases switch. Okay, so if they're both inverted or both not inverted, then the cases switch, and then you just go case by case. I've also put an example for you, the same example that I just did for you, by the way, and I've written out the explanation here for you. Okay, so hopefully that will help. All right, guys, it's been a long one, and if you've listened to this whole thing, congratulations, okay? Like, that's awesome. I really appreciate that. And have a good one. There will be one more thing this week. Remember, I get 3 hours, so there will be one more thing this week before I let you go. Just checking where we are in the outline here. You won't be able to answer all of these questions today, but if you could maybe do the first one, and then tomorrow we can finish it off. Tomorrow's lesson will be very fast because like actually all the tools we need are in today's lesson, so we won't have to reinvent the wheel tomorrow. Okay, or whenever we do the next one. All right, guys, so that's it, and have a good one. We'll talk to you soon.